Hello everyone and welcome back to Basic Biomechanics Tutoring. My name is Chandler McDonald and let's continue with this video series talking about biomechanics, specifically dealing with torques and levers. We're continuing on with chapter 13 from the book. This time we're going to be looking at a problem I cooked up for you. It covers quite a bit of concepts from torques, namely resultant torques. It deals with static equilibrium, as well as some component forces that you'll see with anatomical levers and things of that nature. So let's jump right into the problem and go over some of these concepts. So here's kind of our agenda for today. We're going to be covering mainly these topics here. There we go. And here's the problem. So, a man is trying to curl a 60 kilogram dumbbell, which it's a lot, like 120 pounds. He manages to swing the weight up, he cheats, to a 40-degree angle to the vertically oriented humerus. If his flexion muscles have a maximum force generation of 4,400 newtons in this position, does he curl the weight or does it fall? Well, right off the bat, curling a 120-pound dumbbell, it's a lot of weight. I'm going to guess that it's going to fall, but we need to actually chug some numbers to see what the resultant torque is. So this is a problem dealing with resultant torques, where we have to find torques both on the weight side and on the force generation side. Assume the weight is 33 centimeters away from the axis, bicep insert 3 centimeters away from the axis. Okay, so then we have this little section right here we will visit as soon as we finish the first one, because that's when it gets into different concepts like static equilibrium, components of anatomical levers, that sort of thing. So let's get into the problem. We have a bunch of knowns, and we're solving for an unknown value, which is right here, the torque net. Mass of the dumbbell, distance of the dumbbell, so this distance here, force of the muscle here, and distance of the muscle here. So given this little 40-degree thing. So right off the bat, we're dealing with an angle. We can't assign that the force of the muscle is going to be the perpendicular force. As we know, torque is a perpendicular force times distance. So we're going to have to both solve for this factor of 40 degrees here, as well as here, so that we can get this perpendicular force. Let's try to simplify the picture. There's a lot of fluff in this, and let's clear some of that up. Helps visualize the picture a little better. So we'll do that right now. Essentially, you have the axis here, distance to the weight here, which is coming down here. And you also have force in the muscle, let's just say right about here. And yes, you have 40 degrees here, as well as over here. Like I said earlier, we're dealing with an angle. We need to find those perpendicular forces so that we can actually know their magnitude and go about solving for their torques. So let's do that right now. Oh, well, first off, let's see that the torque, or the rotation, a force in this direction is going to cause a rotation this way, and force coming down this way compared to the axis is going to cause a rotation this way. We have opposing torques. It's not asking for static equilibrium, so they don't have to equal each other. Let's just go ahead and solve. Starting with the weight. So have this vector down here. This is 40 degrees. This we have to solve, which is the mass times gravity, so that we can get force in newtons, which is 588.6 newtons. Okay, but we are looking for this right here. Using the tip to tail method, we're looking for this weight perpendicular or force. Weight is a force. And to do that, we can either take the weight sine 40 degrees, because after all that is this, we're dealing with opposite and hypotenuse, so weight sine 40 equals the perpendicular. Or some people like to put their vector right here. This would just change this to be 50, and then you would take the cosine, or weight cosine 50. They both equal each other, which gives you this perpendicular weight of 378.345 newtons. Okay, so we have one. We're actually already given this distance here. We can solve the torque for this one, but let's try to solve this perpendicular force first, then we can solve for torques, add the torques and see the resultant torque. So let's do that right now with the force. So the muscle, same kind of deal. You got this 40 here. This is force in the muscle. We need to find this perpendicular force here. I'm going to switch colors for this one. Okay, same thing over here. You're given the force of the muscle, 4,400 newtons. It's the maximum amount. Sine 40 degrees or cosine 50 degrees if you draw the vector right here, making this 50. I like to stick with this, just the tip to tail method. It's much easier. So this is going to equal, if this is 4,400, this is going to be 28.27 newtons. And from here, we can solve for the torques on both sides. So let's go ahead and do that. All right, so now we have the torques. Let's talk about direction so that we know what is going to be either negative, positive, eccentric, concentric, whatever. We still need to assign it a sign to know opposing directions and then therefore get the final solution. So we are going to sum the torques to find the resultant torque. Basically the direction of which this thing is going to travel. Is it going to move in a concentric or eccentric action? My guess is eccentric, but let's see by how much. So we need this torque here plus the torque, the muscle, this. Earlier, this is going to be moving in this clockwise motion. So the torque of the weight is going to be in the negative direction. This is going to be moving in the positive. Once again, eccentric, concentric, whatever. We need to assign it direction regardless. Let's go here. So let's plug in these numbers now, or more specifically, 40 Newton meters eccentrically. Because this is in the direction of the weight. So the dude only had about 2/3 the strength to even lift this thing. He's way out of his league. He can't even curl it. He should just drop down maybe 50, 60 pounds.